Hello and welcome guys, my name is Steven, welcome back to my channel, welcome back to the Concurrency in Go course. Now for those of you who are new to this channel, make sure to hit that like button, subscribe to this community if you aren't already, and of course make sure to watch the first videos of this Concurrency in Go course. And if you find any value during any time of this video, make sure to hit that like button and share this video so that others know about it. And also before we dive into any kind of coding, presentations and all that stuff, make sure to check out the GitHub repo where you will find a downloadable zip so that you don't have to write code by hand, so that you can follow along as we progress in this video. And because this topic got a little bit too long, I decided to split this into two videos. And in the first part of this video, we're going to dive into atomics, what are atomics, how to use atomics, and pretty much anything basic and everything you need to know about atomics. So the first question that might pop in your head is, what exactly is atomics? Why are they called atomics? So they are primarily called atomics because of their nature, because they are pretty much like atoms in an electron. They are indivisible, they are the smallest thing you can get. And this is a very important component for concurrency because every operation that happens concurrently has to be atomic, it has to be deterministic, it has to not be divisible or interruptible by some other process which also executes concurrently. If you have heard about or you have been asked about the term acid, well, just so you know, the first letter A stands for atomicity. And what exactly is atomicity? Now, it's very important to understand this term because we're going to operate with this a lot in this course. So within the defined context, something is atomic if it happens in its entirety without anything else happening simultaneously or interrupting that specific process. And again, the key term here is the context that we define. It has to happen within the same context. In a different context, it may not be atomic already. The simplest example of atomicity is probably the operations which you are using in Go or pretty much any other language. Operations like plus, minus, multiplication, division, equal, and all that stuff. So these are the perfect examples of atomic operations, and no matter what, no matter if you execute code concurrently or not, these operations will always execute atomically. Now let's have a look at the plus operator, which most languages out there provide. You might think this is an atomic operation because it's a single operator. However, a bunch of things happen behind the scenes which make this operation not atomic at all. So when you use the plus operator, a couple of things happen behind the scenes. First of all, we have to get the value of the variable which we're trying to increment. Then you have to increment the value that we received from this I variable. And after all, we have to store back the value which was incremented back into this I variable. So again, keep in mind that atomic really means indivisible and uninterruptible while they execute in a specific context that we define. Now let's get a little bit closer to Go and let's have a look at a different example. Let's suppose you have goroutine 1 and goroutine 2 and you have some kind of data which is shared. Let's say both goroutine 1 and goroutine 2 is trying to access that shared data. First goroutine is trying to read the data and the second goroutine is trying to write to the same data. Now the way that we would reason about that is they have to have some kind of mechanism, they would communicate. You would think we might have some kind of locking mechanism in place, which is the way to go. And this is the basic principle of atomicity. We are trying to accomplish something and we don't want to be interrupted by some other process. Now when it comes to Go provides a lot of other types in the sync package which would provide you that locking mechanism. However, when it comes to atomics work a little bit different. They do not rely on built-in data structures which are available in the runtime. They will work primarily with the CPU, meaning the CPU has registers and those registers can store things including data, including addresses and a bunch of other things. Now the best way to compare CPU and the registers is with a box of chocolate. Now imagine you have a box of chocolate and that box of chocolate, as you all know, has spots. Now those spots can be either full or empty. It's pretty much the same with registers. We have a lot of goroutines, they're trying to execute things and they're trying to access things at the same time. Now when they try to access memory, they will basically have to interact with the CPU, then with the CPU registers. So the primary job of a register is to store instructions, store results, and manipulate and store data. So let's get back to our CPU picture and have a look at where exactly these registers fit in. Like in the previous videos, we have the CPU, then under the CPU we have the OS kernel, which will basically communicate with the CPU and all the resources that it controls. And when it comes to CPU registers inside one thread will always be different from registers in a different thread. This will keep things safe and the data is not going to mess around between registers, between threads and all that stuff. So having a look at the same problem, let's imagine this time you have three goroutines. You have G1, G2, and G3. Let's say the first goroutine is trying to increment the I variable by 1, the second is trying to decrement it by 1, and the third is trying to increment it it with 2. And we have an initial declaration of the I variable, which is going to be equals to 0. And this way our code will still execute deterministically. Let's say G2 will execute first, and G1 will get to execute or work with that register, and then in the end G3 will do its job. So this is pretty much how atomics work in a nutshell. And now let's jump into an example where we actually do not respect this principle of atomicity, where in the end we actually get a race condition. So let's create a new directory called race. Let's also create a file called main, and as usual package main and func main. So first of all, let's go ahead and create a wait group so that we wait for these coroutines to execute. I'm gonna say var wait group sync.wait group, and regular procedure wait group dot wait, and in between let's say go func, and let's also say defer wait group dot done, and let's copy and paste this a couple of times. So I'm gonna say wait group dot add right here, and let's call this with the argument of 5 because we have 5 running go routines. And now in order to simulate a race condition, it's enough to read at the same time or write at the same time in at least 2 go routines. And for that, we need some kind of shared variable. So let's go ahead and create a shared count variable. So let's go ahead and create a variable, for example, called count, and it's going to be an int 32. Let's say the first go routine is going to add the value 10 to it. So let's say count plus equal to 10. And now let's go ahead and copy this and paste this in this go routine. Let's say this go routine will attempt to decrement this with minus 15, and let's say this coroutine is going to simply increment this by 1, and let's say the next coroutine wants to level this up, and let's say this one wants this counter to be equal to 100. So right after this wait statement right here, let's go ahead and print the value of this count variable. Let's say something like fumpt print line, let's say count, and let's print the value of this count variable. And now that we have everything in place, let's go ahead and run this example, and you will see the result is pretty much different. It's non-deterministic, as I said before. So if you go ahead and run this example, as you can see, the count is pretty much different all the time. And now let's open up a terminal and run this specific example using the race flag to demonstrate you that it's actually a race condition. So open up a terminal and let's cd into the race example, and let's say go run. However, this time we're going to provide the race flag. So let's say minus race, and let's say main.go. And when you run this using the race flag, as you can see, it says warning data race, and it gives you the struct trace. It gives you the exact location where this happens. This is a data race. It's something we want to avoid. It's something which is bad for our programs. One way of solving this race condition is to use atomics. So when it comes to the atomic package, it will primarily have support for functions which will give you the possibility to atomically and concurrently modify numbers. It will have functions like load, add, store, swap, swap, and compare. And all of these functions will of course work with int32, int64, uint32, uint64, uint.ptr, and of course pointer. Now with all that being said, let's have a look at an example which makes use of some of these functions. So let's say new directory, let's call this basic counter, and as usual a file called main and package main, and of course func main. So let's go ahead and create the wait group first of all. So let's say var wait group is going to be sync.wait group, wait group dot wait. So let's again declare a variable. Let's say var count, this time is going to be an int64. So let's go ahead and say go func, and before we do anything, of course, defer wait group dot done, and because we call done, let's go ahead and say something like wait group dot add, and let's say we want to listen for one go routine right here. And to simulate a little bit of load, let's go ahead and time sleep 10 milliseconds. So let's say time.sleep, let's say 10 milliseconds. Because our variable right here is int64, we're going to use a function called load int64. So let's go ahead and say something like atomic.load int64, and let's also provide in the address. As you can see, it's asking for the address, and let's say ampersand, and we'll provide in the count variable. And as you can see, this function also returns back a value which is int64, so we can go ahead and use this value and print something out. So let's cut this and say fumpt.println, and let's say count in go routine, and let's provide in the specific value. Let's go ahead and run a for loop. Let's say for I is going to go from 0 and I is going to go up to 50 I++. Before this call to for, let's go ahead and run a call to wait group dot add. Let's say we want to wait for 50 go routines. So let's simply say go func, and as usual, let's call defer wait group dot done before we do anything else. We also want to simulate the same amount of delay. Let's copy this time.sleep. Let's paste this over here. And now let's attempt to override this specific counter variable. And there is a specific function in the atomic package called add int64, which is going to do exactly that. So let's say atomic.add int64 64. So as usual, let's provide in the address of this count variable, and it wants the delta as the second argument. So the delta is going to be something like 1. So every time we run this statement right here, we're basically going to increment this specific variable by 1. So as you can see, this one is the reader. Let's call this, for example, reader, and this one will be, let's say, writers. Let's copy and paste this print statement right here so that we create a little bit of distinction after we wait. Change the statement to something like count in main, and let's also provide in simply the value of the count because we no longer need to use atomics. We are no longer running any concurrent operations. So when you run this example, you will get something like that. Count in main is always going to be 50, but count in coroutine is always going to be different depending on whoever or which coroutine writes first to that count variable. So when you run this example, as you can see, you get multiple values in the counting coroutine, and you get a single value, which is 50, because we ran 50 coroutines which attempted to increment this value by 1. So let's simply open up a terminal and let's cd into basic counter, and let's say go run minus race, and of course main.go. And as you can see, we have no race conditions. If you run it again, we have no race conditions whatsoever, which means our code will always execute deterministically, meaning yes, we're gonna have random results because we have 50 coroutines, but the code, or I should say the execution of the code, will always be deterministic. Things will always be in sync. And now that you guys know how to use atomics, what are atomics, let's go back to our race example and fix that using atomics. So again, nothing fancy. I'm just gonna go ahead and copy this example. So let's copy this directory, paste it right here. Let's say race fixed, for example. And all that we have to do right now is call a different function from the atomic package, which will basically override this count variable. So let's say something like atomic, and this time we're going to call something like store, and of course in 32, and as usual provide in the address, and let's say count, and of course provide in the value, which in our case is 10. And we can now go ahead and remove this statement right here, and let's copy and paste this a couple of times. So let's say minus 15, for example. Let's copy and paste this one more time. Let's say 1, copy and paste this one more time. Let's say 0, and let's say for example 100, and let's cd into race-fixed. Let's first of all try and run this without the race flag. So let's say go run main.go as we're used to, and when you run this multiple times, as you can see, we get different results. And if you add in the race flag, as you can see, we no longer have any kind of race conditions every time we run this program. Now when it comes to atomics, and specifically the atomic package, it's not limited to just numbers. You can also manipulate a little bit more complex types atomically and concurrently, types like structs and all that stuff. And that specific type in the atomic package is called atomic.Value, and it will primarily have two methods. It will have a method called load and another one called store. This is why, without too much further ado, let's jump into a couple of examples demonstrating and working with atomic.Value. So let's say new directory, and let's call this one value. So let's first of all dive into a relatively simple example. New directory, let's call this one reader-writer, and as usual, let's create a file main and package main and func main. So first things first, let's go ahead and create that wait group. So let's say var wait group is going to be sync.wait group, and of course, let's call wait group.wait. Before we run anything or call the wait group.add method, let's go ahead and create that shared variable. Var v is going to be atomic.value, and this time around we don't have to call functions on the atomic package. We can simply say v dot, and as you can see, we have the load method, which will give us back the value stored inside this atomic value, and we also have the store method. Speaking of types and more complex types, let's go ahead and create a type which is going to be a struct. So let's say something like type, let's say config is going to be a struct, and let's say it has something like a, and a is a slice of ints. Now that we have the specific type, let's go ahead and run those go routines, the readers and writers. So let's first of all take care of the writers. So here we're going to have defined the writer, and the writer, as I said before, is going to be a go routine. So let's say go func, let's say for, and we're going to have something which runs infinitely. And let's say we have some kind of a loop variable. So let's say var I is going to be a simple int. Let's say I++. Now let's go ahead and create an instance of this config type. So let's say config is going to be config, and let's say a will be a slice of int. So let's say I+1, I+2, I+3, I+4, and let's add one more. Let's say I+5, and let's format this a little bit. And of course, we want to store this config variable onto this v. So let's say v.store, and store accepts an interface. So let's go ahead and pass in config. Readers are going to be placed right here. Before we run run this inside a for loop. Let's say wait group.add, and let's say we want to run 5 readers. We only care about waiting for this specific 5 readers. We don't really care about this one right here. This one will get destroyed with the main function. So let's go ahead and run that for loop. So let's say for I is going to be from 0, I goes up to 5, and of course I plus plus. So as usual, let's go ahead and run the function using the go keyword. Let's say go func, and before we do anything, let's say defer wait group.done, normal procedure. So let's go ahead and say something like v.load. And the thing about this load method, as I said in the beginning, is the fact that it returns an interface, and sometimes that's not convenient. Let's say we want to access the specific field, which is A. We can't really do that. Let's say we want to store this inside config, and let's say we want to access the A field. If you try and access that field, is not going to work because obviously this is an interface. So what you want to do is to do type assertions. So let's go ahead and say we think this is of type config. So we're going to do a dot, and inside parentheses, we're going to say it's of type config. And now let's go ahead and print the specific value which we got loaded from this atomic.Value. So let's say font print line, let's say config is going to be config. If you run this example, you will probably run into a panic because when you do type assertions, you also have to check the value which you got from the specific type assertion. So if you run this example, as you see, it's going to run inside a panic. Obviously, in the beginning, before we get to write anything here, this specific value is going to be nil. And because we assert or we think this is of type config right here, it's actually not. And because of that, it's going to panic. And as you can see, the panic says interface conversion, interface is nil, not main.config. And all we have to do is use the comma OK idiom. So let's say if it's not OK, it means we got a different type. So I'm going to simply say log.fatalf. So I'm going to say something like received a different type %T and providing this config variable. And when you run this example, this time around, it's going to log.fatal saying received a different type main.config. Now to avoid that, all we really have to do is after we initialize this variable, try and write some kind of default value to it. So that's done very simple. Let's just say v.store and let's store an empty config, something like config. And let's say A is going to be a slice of int, which is also empty. Now, like we did in the previous examples, we want to make sure this example doesn't have any kind of race conditions. This is why let's open up a terminal, cd value reader writer. Let's say go run -race main.go. And as you can see, it doesn't have any kind of race conditions, which is good, which means the output of this or the result of this specific program is always going to be deterministic. Now, if you did not like the reader writer example or you think was not that interesting, let's jump into another example. So let's create a new directory and let's call this calculator. And of course, create a file called main. Let's say file main and package main, and of course, func main as usual. So right before the main function, I'm going to go ahead and create a type called calculator. So let's go ahead and say type calculator, and let's say it's going to be a struct. So let's say we want to store a field called res. Res is going to be atomic.Value, which again is there to store the overall count. And now let's jump into creating the methods for this specific type. So let's go ahead and say func. Let's say C is going to be a type calculator. Name this one add, and it's going to be float64. Duplicate this couple of times. So let's say duplicate, duplicate, and duplicate. This is going to be called subtraction mul, and let's call this one div. So let's go ahead and fill out the add method. First of all, c.res, let's say store, and we want to fetch the value of this specific atomic value. First of all, then we want to add to that value. So let's say something like c.result, which is an existing function, but we will create this soon, plus n, and let's copy this. Let's paste this right here. Let's say this one will decrement. Let's say this one will multiply it by n. So let's say multiplied by n, and this is going to divide it by n. And of course, if n is 0, for example, we want to panic. So let's say panic, and let's say something like cannot divide by 0. Now let's go ahead and fill out this specific result method, which we will also use inside the main function. So all that we really have to do is copy this specific receiver, for example, not to waste a lot of time on typing. And let's say this is going to be called result. We only want to return this float64. So like we did in the previous example, let's say something like c.res, and let's say load r, and let's say OK, because we are going to do some type assertion. And let's say this is going to be a float64. 64. If not okay, we want to handle this. So let's say something like panic, and let's say operating with a wrong type. And at the end of this function, let's go ahead and say something like return R. We want to avoid this type of panic right here. This is why let's go ahead and create a constructor function which will initialize the specific type. So let's say func new calculator, and let's say it will return a calculator. Let's say C will be a calculator, and let's return the specific C, and in between let's say c.res.store, and we want to store something like float 64 of 0, and this will ensure we don't get any kind of panics here when we're trying to do type assertion. And now finally that we have all this specific calculator put together, let's go ahead and use this inside the main function. As usual, normal procedure, we want to wait for the go routines. This is why we need some kind of wait group. So let's say for our wait group is going to be a sync.wait group, and of course wait group.wait. Before that, let's go ahead and say C is going to be a new calculator. So before we run go routines, let's say wait group.add. So let's say 5, and now let's go ahead and run these go routines. Let's say go func. We're going to keep things very simple. Before we do anything, let's say defer wait group done, and let's copy and paste this 4 times. Paste, 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 and paste. And now let's go ahead and fill the details. So let's say c.add. Let's say we want to add the value 10. Copy this, paste it here. Let's say this one wants to subtract 5. Let's say this one wants to divide this by 3, and let's say the next one wants to multiply this by 4. Let's copy this again. So let's say we want to do something like add, and let's say 13. Now all that's really left to do is after we wait right here, we want to print the result. So let's say something like fumpt print line, and let's say result, and go ahead and say something like c.result. And this is pretty much it on this example. Let's go ahead and run this. So when you run this example, as you can see, every time when you run it, we're going to have pretty much different results. And again, let's cd into value into calculator, and let's say go run, and providing the -race flag. And when you run this example multiple times, as you can see, it doesn't have any kind of race conditions. And this is pretty much it on this specific calculator example. Hopefully this was a little more interesting example as to how to use atomic.value. And now let's go ahead and cover a couple of issues or things you have to be aware of when using atomic.value. So as you saw from previous videos, getting a panic in your program will kill your program instantly. So this can happen with atomic.value as well. So let's go ahead and explore a couple of examples, and let's say new directory. Let's call this one panic. And as usual, let's create a file. Let's call this one main, and as usual, package main, and of course func main. First of all, let's go ahead and create a variable which is going to be atomic.value. So let's say var v is going to be atomic.value, and now let's try and store some value inside this specific atomic value. So let's say for example v.store, let's say we want to store the number 1. When storing values in a specific atomic.value, you must always store values of the same type. The moment you call the second store and it's going to detect that it's of a different type compared to the first store, it's going to basically panic saying types are inconsistent or something like that. Let's simply go ahead and duplicate this call, and let's call it with the string 1, for example. And when you run this example, you will run into a panic. So when you run it, it says sync atomic store of inconsistently typed value into value. A different panic you might get is if you try to store nil. Let's say you comment this one out, and let's say duplicate this. Let's say we try to store nil. Let's comment this one out, and let's try and run this example. When you run this example, as you can see, we also get a panic saying store of nil value into value. Sometimes using atomic.value, things may not be atomic. Things may actually run into race conditions. So let's create a new directory. Let's say new directory. Let's say not atomic, and let's create as usual a file called main and package main, and of course func main. So first things first, we need some kind of wait group as usual. So let's say var wait group is going to be sync.wait group, and let's call wait method. So let's say wait group.wait. We need that atomic value. So let's say var, for example, val is going to be atomic.value. And now because we are using atomic.value, let's go ahead and create some fancy type. For example, type student, and let's say it will be a struct, and let's say student will have a specific field called grades, and grades will be something like a map of let's say string to integer. Let's go ahead and store the default value. So let's say something like val.store, for example, and let's say it's going to be an empty student and grades will be an empty map. Now let's go ahead and proceed with the go routines. Let's say we want to run 3 go routines. This is why let's say wait group.add and let's provide in the number 3. Let's say go func, say defer wait group.done, paste this a couple of times. First things first, we want to load the value which this atomic value has. So let's say something like s is going to be equal to, let's say val.load. So let's say this is going to be of type student. And now that we have this specific value, you may think the simplest way to achieve this specific task is to simply say something like s.grades, and let's say we want English, and English is going to be equals to 10. Let's simply go ahead and copy and paste those 2 lines. Let's say math is going to be equal to 8, physics is going to be equal to 7. And now that we have all this in place, all we really have to do is after we wait, call load method again. So again, not to waste a lot of time, I'm simply going to copy that line, paste it over here, and we have an instance of student. And now let's simply say something like font print line, for example, let's say s, which will print that map. Again, when you run this example, as you can see, we pretty much have accomplished whatever we wanted. To check if this program is running atomically and it doesn't have any kind of race conditions, you're right. Let's open up a terminal, cd into value, and let's say not atomic, and let's say go run and provide in the race flag. And as you can see, we have a race condition, or I should say couple of race conditions. We can access the value which is student, but once you start accessing things inside the student type, you'll run into race conditions and things are not atomic anymore. So to fix that, it's very simple. First of all, I'm going to go ahead and comment all these out. So let's say something like m is going to be equal to s.grades. I'm going to copy this statement and replace this with m. And now all we have to do is simply say something like val.store and providing a new student. Let's say student, and student is going to have grades, and grades is going to be this m which we have played with. I'll simply go ahead and copy and paste this a couple of times. So let's say paste it here, and let's also say paste it over there. Let's say math is going to be 8, and let's also change this one with physics, and let's provide in the value 7. Even if you try and keep this thing a little safer, we're still not solving the problem. We're still gonna get something like concurrent map rights, because this is exactly what's happening here. Even though we copy this map over here as a value, this is still a pointer behind the scenes. So as you saw, we got those issues regarding concurrent map rights. However, when you open up a terminal and run this example using the race flag, it will not complain about anything. It will say we don't have any kind of race condition. So let's say cd into value, and let's say not atomic, and let's say go run, providing the race flag. And as you can see, running this multiple times is pretty fine. We do have that error regarding concurrent map rights. This is why we'll solve this problem once we dive into mutexes, which are the exact solution for this specific approach. Now you may think inside the atomic package, there's no wonder it's mostly full of functions which work with numbers, and we only have atomic.Value, which allows us to work with complex types. Now what would be the difference in memory/performance if we were to benchmark storing an N64 atomically using store in64 or store that in64 using atomic.Value? If you are as curious as I am, let's jump into another example where we're going to play with a couple of benchmarks which we already have experience with. So let's say new directory, and let's call this one benchmarks. Let's say new Go file. Let's call this one number underscore versus underscore value underscore test.go. Let's say func benchmark. Let's say store and 64. B is going to be pointer to testing.b. So first of all, let's go ahead and create a wait group, which is going to wait for all these go routines to execute. So let's say var wait group is going to be async.wait group. And now let's go ahead and say wait group.wait. Let's say for I is going to start from 0. I is going to go up to b.n, I++. And we're going to have very simple go routines. Let's say something like go func. And of course, before we do anything, let's defer wait group.done. So let's say something like atomic.store in 64 and providing the address count. And let's go ahead and create that variable. Right after the wait group declaration, let's say something like var count. And let's say it's going to be an N64. And now let's provide in the value that we want to store. So let's say something like N64. And let's provide in the iteration number. So let's say I is going to be an int, and let's go ahead and pass in I. Let's simply go ahead and copy this and of course paste it. Let's say value, and of course instead of this in 64, let's say something like v is going to be atomic.Value, and instead of this call to atomic store in 64, of course we want to call something like v.store and 64 and providing this iteration variable. And one last thing that we forgot to add in both of these benchmarks is to call wait group.add, and let's call this with b.n, copy this and paste this right here as well. So as usual, I'm gonna open up a terminal and let's go ahead and cd into benchmarks, and let's say something like go test minus bench argument, providing in the current directory, which is dot. When you run that, it's also gonna complain because we are using Go version 1.16, and for that we need to initialize this go mod init benchmarks. And now let's run again that command. So go test minus bench, and when you run this, it's going to run the benchmarks. And as you can see, we do have a slight improvement. We're going to have a small increase in nanoseconds per operations, and we're also going to have a very small increase in the number of iterations that we have run, which proves again that using functions when dealing with numbers is a little bit faster than using atomic.Value. All right, fellas, this is pretty much it on the part 1 of this topic. Hope you guys enjoyed it. Now, because this got a little bit too long, we have to wrap this up and see each other in the second part. So I'll see you in the second part of this topic. Peace.